obviously, one of the big ones is nomenclature. You know, in Chem 1B, I'm going to expect everyone to have nomenclature down. But since there are a lot of different Chem 1A instructors, I'm not exactly sure what nomenclature you covered in Chem 1A. And so we'll talk a little bit of review initially for nomenclature. For example, if we look at the cations, and we're looking at the monatomic cations, single atom cations, then we have monatomic cations with fixed charge. With fixed charge, then the formula is easy. For example, this one, Na plus. So we can see what the charge is going to be just based on the periodic table. This group, or this column in the periodic table is called the alkali metals. All the alkali metals have a what? Plus one. And the name of that would be sodium cation, sodium ion. Calcium would be a fixed charge. What's the charge on calcium? Scandium, fixed charge or variable charge? Scandium, it turns out, is a fixed charge cation. There's only one charge that shows up. And do you know what that charge is? 3 plus. Titanium, fixed charge or variable charge? Titanium is variable charge. And otherwise, if you called it a fixed charge, what charge would you associate with titanium? 4 plus. Titanium, in fact, titanium 4 plus is the most common charge on titanium. But if you think about a titanium 4 plus, that means we'd have to strip 4 electrons off of titanium. Now, stripping 1 electron costs energy, right? What do we call that energy that it costs? Ionization energies. And ionization energies, there's a definition. It's the amount of energy that's required to take an electron or remove 1 electron. And about how much energy is that? What's a typical ionization energy? Or what do ionization energies range from? What do you think? Ionization, like if I said, I think maybe around 25,000 kilojoules. Does that sound like a reasonable number to you? 25,000 kilojoules. Well, you gotta have, does it sound reasonable or does it sound off to you? Off? What would be a more reasonable range, or what would be a more reasonable ionization energy? And you're going, this is ridiculous, because can't I just look up the ionization energies? Why are you asking me this when you can look it up? The reason I'm asking you this is yes, you can look it up, but it's important that we have some kind of reference numbers memorized. There is utility in memorizing these numbers, because then you can give them some thought. Do they make sense? Do they not make sense? Or whatever. You can analyze them a little deeper. If you're just in the habit of looking things up, then you don't really understand things at a deeper level. And so the first step in understanding things at a deeper level is just, do you have to memorize every single ionization energy? No. What we want is we want some kind of maybe average ionization energy or range of ionization energies. Ionization energies range from this to this, right? And the reason we want to do that is so that we can understand things a little bit at a little bit more deeper level than just straight memorization. Because it's like you go buy a car. This car is going to cost you $250,000. It's low mileage, hasn't been used that much or something. Does that sound reasonable to you? For a used car you want to use to commute back and forth to school? No, that doesn't sound reasonable at all, right? But that's what happens in science. What happens in science is that people don't care about the numbers. It's like going shopping for a car and not having any clue what a reasonable number is, right? And so it's not that we have to do this for everything, but we want to do this for some things. And so we got ionization energies to deal with. Some things have low ionization energies, some things have high ionization energies. If we look at the periodic table, you know, well, forming an ion, is forming a sodium ion, oh, why did it log me out? I'm having computer issues. This projector is totally washed out. I don't know why. Maybe I should just turn this around. Easier to see that way. But what's low ionization energy in the periodic table? What's high ionization energy? What do you think? Everything to the left. The left would be lower, that is easier to ionize. Right? What would be the easiest to ionize? Periodic table. Yeah, right, Eric is down. So something like francium, although we don't talk much about francium. Why not? This member of the group is a little different than the other members. Do you know why? Yeah, francium's artificially. Francium is a radioactive atom, so it's artificial. And so we don't do that much chemistry with francium. So we'd say cesium, because cesium's stable and it's fairly common. So cesium would be the easiest. You can just memorize that, but do you want to just memorize everything? And what is the ionization? Ionization energy is under 500 kilojoules per mole. So 500 kilojoules per mole would be at the low end. What would be at the high end? What would be the hardest to ionize? Yeah, it would be a noble gas. Which of the noble gases would be the hardest to ionize? Helium is correct. Helium is correct. And so what you did there is you tried to use some kind of patterns because, there's different ways we memorize. You can memorize it using flashcards, right? You can memorize different things, but, there's such a big push away from memorization. But it turns out that memorization is an important part of learning chemistry. And so I do this two-pronged approach. One is just straight memorization. But that's not satisfying. I mean, there's too much stuff to memorize. You're not going to memorize it all, right? What would be much better is if we could just predict it using theory or a theoretical approach. And so if we can use it based on theory, then maybe this, maybe if I asked you, hey, what's the first ionization energy of titanium? And you go, wait a minute, I can calculate that using my knowledge of the theory of chemistry. And I'll just punch some numbers in my head and spit out the ionization energy for you. Have you done that? Have you done that? No. Why? Well, one, what is the theory that you would use to determine the ionization energy of titanium? Well, what is the theory that you would use to do it? If you wanted to, I don't want to memorize it, I just want to calculate it. And so you would use the theory that underlies chemistry. What is the basic theory that underlies chemistry? This theory explains things from ionization energy to, or that explains or describes things from ionization energy to intermolecular forces to bonds, reactivity. What is that theory? Chapter 8 was a theory. Chapter 8 dealt with this theory, Chem 1A. Well, maybe I should back up. Let's go to chapter 1. Let's talk a little bit about the scientific method. Although I don't follow Petrucci's, but this is what I found most people do. I did, and other people around me did, as far as science goes. And the scientific method begins with what? A lot of people say it begins with a hypothesis. Okay, so I'm going to hypothesize the theory of chemistry. What is my hypothesis? They said, okay, guess. Well, I'm going to guess the theory of chemistry. What is my guess? What would be your guess? It's kind of ridiculous in a way because I don't know, would it just be some wild guess, or would it be some educated guess or random guess? What kind of guess is it? And so it really isn't a guess. I don't really like that word, guess. That's what somebody said this morning. The scientific method starts off with observation, right? Observation, and then it goes to what? From these observations, then. Well, I'll tell you, you could go to hypothesis, but it's hard to go to hypothesis straight from observation. It's like, you know, all this nomenclature that we do or whatever else, sometimes it's all mixed up, and then you have to think about these things. You know, this is why you do some memorization of certain things, like observation, the H atom, spectrum, red, orange, yellow, green, blue, indigo, violet. One line in the red, one line in the green, one line in the blue, one line in the violet. This blue is very faint. Give me your hypothesis. So the observation is the line spectrum. Everybody knows the line spectrum of the hydrogen atom, right? 4 lines. Give me your hypothesis. It's not easy to do, right? And so normally that's too difficult to jump. And so typically what we'll do is we'll go from observation to something else. What would that something else be? No, not even questions. You're just looking for this, and what you're looking for is some kind of pattern. Yeah. Pattern or trend. Typically, when we do a pattern, we like to define the pattern mathematically. A mathematical equation would be the simplest definition of anything. And so we try to look for a mathematical pattern here. Do you see a mathematical pattern? No, and so this is why, you know, this first number, 656, this is why you memorize. You memorize these numbers so you can grind them, you know, so that your subconscious can work at making some kind of connection. You say, okay, what are those numbers? Well, you know, let me look it up. You know, the people who were working on this, they didn't look it up. They knew the numbers. They knew the numbers, and they're trying to work things out in their head to come up with this pattern. And so the importance of memorization is, okay, we got a pattern like this, let's memorize this, and then let's try to figure out what it is. And it turns out that this pattern here fits a simple mathematical equation. Do you guys remember that equation, the Rydberg equation, or Rydberg equation? It fits a mathematical pattern. And that pattern, we could call it a law. You know, if it fits that pattern, there aren't any exceptions. We have 2 different things. We have rules and we have laws. Which one is more rigorous as far as a law or a rule? A law. You know, a law we wouldn't expect too many. Let me give you an example of a law. A law would be PV equals nRT, the ideal gas law. Give me an example of a rule. You know, some kind of pattern with lots of exceptions. Nomenclature pattern? Yeah, nomenclature. Nomenclature sometimes it just seems so arbitrary and random, you know, how things are named. But sometimes there is a pattern there. It depends on who did it. Like, here, oftentimes we call these empirical equations. Empirical, do you know what empirical stands for? Empirical stands for, this equation is derived from observations, not from theory. Did someone derive the ideal gas law from theory? No. Not the original ideal gas law. Later on, people used theory to derive it. But Now, this came from observation. What observations? Charles' law, Boyle's law, etc. Those observations led to this law. Some rules would be like solubility rules. Did you have to memorize the solubility rules? Yeah? How many people had to memorize the solubility rules? Not that many, only 4, 5, 6. Everybody's going to have to memorize the solubility rules. All right, so memorizing solubility rules is the first step in recognizing a pattern. Did you notice any pattern to the solubility rules, or was it just totally random? Just kind of arbitrary. Or did you see a pattern? Well, the first step is, for the people who have to look up the solubility rules, they're never going to see this pattern necessarily because they don't know the observations. But the first step in looking for these patterns is to just go ahead and just memorize it. It's like this. Did they know what the equation? Did they know the Rydberg equation before they even? No. It came from looking at this, and then eventually they came up with the Rydberg law. Whatever, it works. Anyway, we'll continue on here. After laws comes what? After laws comes the hypothesis. And so I know, like in biology, they always start with the hypothesis first, but here we're going to start with the observations first. They start with the hypothesis first because they're just jumping ahead. They're just skipping all this other stuff, but they do it. They have to do it. They have to know what the observations are in order to come up with a hypothesis. What is the hypothesis? A hypothesis is some kind of fundamental description or fundamental explanation of this. So if we go, what was the hypothesis for this? Why did gases behave in this particular manner? And so somebody hypothesized something called kinetic molecular dynamics, which eventually led to kinetic molecular theory. So we have kinetic molecular theory. Kinetic molecular. Oops, I don't want that. I want theory. Theory comes at the end. And so these are the basic steps. But, when we do science, sometimes the theories is too hard. So, for example, if I wanted to know the ionization of energy of titanium, I'd love to be able to use theory in order to predict it, what that is. And so what is the theory that I'd use? Well, the theory that I'd use originated from this observation, the hydrogen atom line spectrum. The hydrogen atom line spectrum eventually led to the development of the theory that underlies chemistry, which is the number one thing. If the number one thing out of chapter 8 is this theory. That's the number one thing out of chapter 8. I'm sorry? Go ahead.
Dalton's atomic theory?
No, that's the number one thing out of chapter 2, is Dalton's atomic theory. Dalton's atomic theory is just this kind of hard shell, but what's inside the shell? It's like, you see the shell of an automobile, but what's inside the automobile? This is the theory that's talking about what's inside the automobile.
Electrons inside an atom?
Yeah, and what's the theory called?
Orbital theory?
It's not called orbital theory, but orbitals come out of the theory. Valence bond theory comes out. Valence bond theory is a specific application of this theory to bonding. In fact, you have to, this is the other thing you need to review. You need to review bonding. There are two bond theories that we use. We use valence bond theory and we use, both are quantum mechanical based. Valence bond theory and molecular orbital theory. What's the difference between valence bond theory and molecular orbital theory? Your color? One's simpler. Which one's simpler? Which one's been simplified? The valence bond theory. Valence bond theory is simplified. I called it what? The quantum mechanics light version. Valence bond theory is the quantum mechanics light version. Whereas molecular orbital theory is the quantum mechanics full. And the theory is, Eric? Got it. The theory is,
Which one? Quantum?
yeah, quantum. Quantum chemistry or quantum mechanics. And so, so I could use quantum mechanics. You know, you had a chapter of quantum mechanics, chapter 8. Now, can you tell me what the ionization energy for titanium is going to be? No. Why? Because it's just too hard, those calculations. And so we have to do a two-pronged approach. Otherwise, we can't do anything. You know, you heard of the Schrodinger equation? Schrodinger equation is the equation of quantum mechanics. The Schrodinger equation can only be solved exactly for the hydrogen atom. If we want to do anything more complicated, we got to do a mix of things. We got to do a multi-pronged approach. And so what we're doing here is we don't want to just do straight rote memorization. Memorization. We don't want to just do straight memorization of everything, you know, but we have to memorize some things. Like, for example, what I said is you want to memorize some of the range or the averages, but not the individuals, so that you have a better idea of where to place things in terms. So, for example, sodium, is it easy to ionize or hard to ionize? Sodium metal, sodium solid. Easy or hard to ionize? It's easy to ionize. A lot of people say sodium gives up its electron, but it doesn't totally give up the electron because it's going to cost you. How much energy is it going to cost you to ionize a sodium?
Well, the first ones would be easy, but then after that, it's
Well, okay, the first one's easy, and what is it? This is like, okay, hey, I'd like to buy this car. Well, it's cheap. You know, I'm going to sell this to you really cheap. And you go, well, how cheap is cheap? Well, really cheap. You're going to get it. Super deal, right? This is what the scientists, if you answer a scientist, it's easy, they're going to go, well, how easy is it? Easy is not good. Easy is not a good answer. Easy is way too qualitative, you know? And so they're going to ask you, well, how much? It's like going to buy a car. It's cheap. Well, you don't know how cheap is, right? And so you have to have some numbers memorized. Otherwise, you can't talk in science, right? And so how easy is easy? Easy is like 500 kilojoules. Is that really easy? What can you do with 500 kilojoules? How much water can you heat up with 500 kilojoules? Well, an awful lot of water, right? 500 kilojoules. And so it's not so easy, but ionizing the second one is how much harder? Is it twice as hard or 10 times as hard or 100 times as hard? So if we ionize the second electron off sodium ion, we'll form sodium 2 plus. Is that possible? Is it possible to form sodium 2 plus? Yes, but highly unlikely because it costs
more energy.
Yeah, and how much more energy? Well, you could say lots. But I'll tell you, I went to a conference where somebody said really little and talked in terms of really little or a lot. And in the audience, there's this one professor from Caltech who's very famous. He's like the founder of ultra-high vacuum technology. And this was just a student giving the presentation. And he started asking, about the numbers. But he had no idea. He was trying to explain things in little bit, and lots, and all these other terms. And it was a unfortunate, uncomfortable situation. But it's not that you have to have every number memorized, but there's certain key numbers that you should have memorized. For example, sodium. Sodium, it's pretty easy. That is, for example, we're talking about light. Did I erase it? No, I still have it. Will red light be enough energy to ionize a sodium atom? Do you know how much energy red light has? Do you know how much energy violet light has? Will violet light be enough energy to ionize sodium? In other words, if I have some sodium metal, do I need to protect it from visible light? Or can I just leave it exposed to visible light? What do you guess? No, you have to protect it. You have to protect it from visible light. Otherwise, visible light has enough energy to start corroding your sodium metal. Those types of things we can get just by learning some some numbers. And then we could do much more. By memorizing a little bit, hopefully we can look for patterns and we can do a lot more. It's not that the theory's a challenge, so what we do is we don't do straight memorization. If you did straight memorization, then you're going to have difficulty because there's too much stuff to memorize. So what we do is we do a blend of memorization and theory. In other words, sometimes we don't even have to understand the theory, we just look for the patterns. And that's it. And so that brings us to the continuation for nomenclature. Here. So let me just tell you, the first ionization energy, it's going to be hard because this is going to vary from about 500 kilojoules to about, helium's the hardest to ionize at about 2,500 kilojoules, let's say. And so it's somewhere in between there. I don't know exactly what it is, but it's somewhere we can kind of guesstimate where it's going to be. Now, if I do the first ionization energy, it's going to cost me that. When I do the second ionization, so I take off one electron, is the second one going to cost me the same amount of energy? Is it going to be harder or easier to ionize? It's going to be harder to ionize. And then typically, if you look at the pattern, it's about twice as hard. It costs you twice as much energy. That is until we get to the core. So we go from titanium +1, +2, +3. Once we do that, +4. Once we do that, we've lost all the valence electrons. And then when I start to try to go to titanium +5, how much more energy is that going to cost? Do you expect to see titanium +5? No, I don't expect to see titanium +5, just like I don't expect to see sodium +2. You can do it, but what would you need to do it? You need a lot of energy because taking the first electron off, sodium about 500, taking the second electron off, more like 5,000. This is guesstimate, by the way. But we're talking about 10 times as much energy, or more, or less. And so it's not going to happen. And it's the same thing here. What do I expect to see? Titanium's variable charge, because removing 4 electrons, each time it doubles, by the time you get to titanium +4, it's going to cost you a lot of energy. Well, it turns out titanium +4 is the most common oxidation state, so it's achievable. Going to titanium +5 isn't going to happen. But it does cost more energy. So what we see for titanium is we see +1, +2, +3, and +4. There are 4 different charges that you find for titanium. Whereas vanadium, you just see 1. Not vanadium. Scandium, you just see 1 and +3. How about vanadium? What do you think the charge on vanadium is? The vanadium's right here. +5. But is losing 5 electrons easy? No, it costs a lot of energy, so we're going to see variable charge here. Vanadium is going to range from +2 to +3 to +4 to +5. And so we see variable charge. When we have variable charge, we have to write the name plus the Roman numeral. And so the same thing, chromium, variable charge, manganese, all these are variable charge until we get to where? No, copper is variable charge too. Do you know what the charge on copper is?
+2.
+2 is the most common charge, and?
+3.
No, +1. Copper is +1 and +2. Zinc, however, is not. Zinc is +2. Zinc is fixed charge. And so zinc is always fixed charge, so you make flashcards for that. Zinc is always +2, or you can write it down over and over. Zinc is +2 to grind it into your memory, long-term memory. But what we want to do is we don't want to just do memorization. For example, is there some kind of pattern to this? Is there some kind of thing that we can look at, or some kind of theory that can help us understand this better so it's not just straight memorization? And so one of the things that we can do with zinc is we can look at its electron configuration. The electron configuration of zinc is argon. What is it? 4s2, 3d10. So if we lose 2 electrons, which electrons did we just lose? It's valence. Which would be considered the valence electrons on zinc? The 4s2. And so we'd lose the 4s2. And so when we go to zinc 2+, Zn2+ is going to be argon 3d10. If we try to go to zinc 3+, we'd have to lose a a D electron. And the problem with that is a filled subshell or a filled sublevel, like a 3D, is somewhat stable. And so this would be like removing a slice of the cake here. We don't want to ruin our perfect cake, which is spherically symmetric, at least. And so here we can see that, yeah, it makes sense that Zn goes to 2 plus, and that's it. It's a fixed charge. Why do we want to go? I mean, why didn't we just stop at Zn plus 1? Why did we go to Zn plus 2? Because this isn't going to cost you twice as much energy to ionize a second electron. No, this is going to be way unstable. Zinc is the most stable. And then we have the ionization energy, which we call IE1. So Zn plus 1 is less stable. And then we have ionization energy 2, which is about twice as big. I should make it twice as big here. So let's go like this. This will be Zn plus 2. Which one's more stable? In terms of this, in terms of gravitational potential energy, here's my zinc. Here's my zinc 2 plus, and here's my zinc plus, and here's my zinc 2 plus. Which one's more stable? Zinc. So it's not going to zinc 2 plus because of stability. This is at the end of chapter 12. At the end, the reason why it stops at Zn 2 plus is because of what? It's not because Zn 2 plus is more stable. Clearly, it's less stable. Zn 2 plus is less stable. It's this many kilojoules of energy. The reason why, sodium, everybody says sodium gives up its electron, gives it away. It doesn't give it away. Sodium is going to cost you 500 kilojoules to take its electron. Is 500 kilojoules nothing in terms of energy, or is it significant in terms of energy? What can you do with 500 kilojoules of energy? You could heat up a little bit of water, like a drop of water, or you could heat up a lot of water. You could heat up a lot of water. Is 500 kilojoules nothing? No, it's significant. And so why does it happen? Why is it this? In Chem 4, they call this Dr. Jekyll and Mr. Hyde. Which one is Mr. Hyde? Which one's Dr. Jekyll? Dr. Jekyll is the mellow, sedate one. Mr. Hyde is the violent, unpredictable one. Which one is the stable one? Sodium ion or sodium? Sodium ion is the more stable? And then somebody's going to ask you about energies. Somebody's going to say, wait a minute, I don't believe you. This is what's going to happen at the conference. I don't believe you. Sodium is here, and then we have to add 500 kilojoules per mole to get to sodium plus here. How is this one more stable? This is called an energy level diagram. We plot energy on the y-axis. The higher we go, it's like gravitational potential energy. The higher you lift this iron, the higher the energy is. Okay? So if I drop it from here versus if I drop it from the ceiling, this is a lot higher energy, right? So you tell me, this is why you have to know numbers. You have to know numbers because somebody's going to ask you about this kind of stuff as you progress in science. And you don't want to be like the guy I saw, who never looked at the numbers. And so you don't, it's not like you go all gung-ho, you just do a little bit at a time. But obviously you don't have to know all the numbers. You can say, I don't know. I don't know why. I just know that this is Dr. Jekyll, the mellow one, and this is Mr. Hyde, the violent one. But why is the violent one lower in energy? And the answer is in chapter 12. Because we don't just form sodium ions. If you just form sodium ions and try to bottle them, it's impossible. Can you have a bottle of pure sodium ions? I don't want the chloride, just give me the sodium. I don't want to waste any money on chlorides. Is it possible to get salt? I'd like to buy the salt, but I see, it's 10 cents a pound, but just keep the chlorides. I'll just take the sodiums. Can you do that? No. And so the reason is no, this is not stable. How it gets stable is it forms bonds. And so bonding is very important in this discussion. And so in chapter 12, they said, well, if it forms bonds, the higher the charge, the stronger the bond. And so I don't know if in Chem 1A, your Chem 1A instructor assigned this. I don't know. Eric, did I assign this problem? I'm sure I assigned it because I assign this problem every semester. But this one was this. If you could make a sodium chloride lattice, this is at the end of chapter 12. You remember the Born-Haber cycle? Probably not. But you don't have to review Born-Haber cycle for Chem 1B, although knowing a little bit about it would be helpful. But the higher the charge, the stronger the lattice, the stronger the bonds. And so what we could do is, in fact, there's something called, do you know the law that describes the electrical attractions, what it's called? If you had physics, you'd know of that. Coulomb's law. Coulomb's law is in Appendix D in our textbook. So if you want to take a look at Coulomb's, it's mentioned briefly in chapter 2, but it's mentioned more deeply in Appendix, not Appendix D, Appendix A. I think Appendix A. Well, anyway, if the charge doubles, the strength of the bond, if the charge doubles, the strength of the bond should double as well. If the charge on the cation doubles, the strength of the bond doubles. If the charge on the anion doubles, so if we double the cation charge and double the anion charge, then we get 4 times the lattice energy. And so the homework problem is this. This is a hypothetical problem. The hypothetical problem is calculate the lattice energy if you made sodium a +2 cation and chlorine a -2 anion. And this one, getting the +2 is going to cost you a lot of energy. And then adding a second electron, this second electron to chlorine goes into the next shell. That's going to be unfavorable. That's going to cost you energy. But is the cost and the energy worth the payoff in return? Because what nature tries to do is it tries to minimize the energy. It's like this. Nature is willing to invest. It's willing to invest this because the return is going to be greater. And so this is like you invest $500 or something, you're going to get $600 back. Well, you just got $100 extra, right? That's how nature works. If you invest $500 and you lost it, you think it's going to happen? No, so there's got to be a return. And so this is what the return is. The return is in terms of bonding. And the bonding is going to be heavily influenced on the charges. So we need to know the charges on the ions, right? And we need to review bonding. And so do that. And so you'll need to review some of Chapter 8, the quantum, in order to understand the bonding theories. The bonding theories would be in terms of Coulomb's law, valence bond theory, and molecular orbital theory, which we're going to use. Primarily, we're going to use valence bond theory because it's simpler. It's a simplified version of the quantum mechanics of bonds. But we also need to do this, So, it's not just straight memorization because you should have had this already memorized. Zinc is a fixed charge. What else is fixed charge? Once we get from past scandium, all these term variable charge. All these. Silver is always +1. And cadmium is always cadmium is always +2. Now silver is easy because you'd see it. Hey, silver. Silver is argon, 4s1, 3d10. And so if we just lost that 4s electron, then we're going to get a fixed charge, silver plus, which is going to be argon, 3d10. So it makes total sense. But then somebody's going to ask you, well, if that makes sense, what about copper? Oops, I'm sorry, it's not argon, it's krypton. I'm thinking. We got to go one down. Sorry, krypton. change this. This is going to be 5s1, 4d10. This should be krypton, 4d10. Okay. Now, it should be okay. Yeah. What about copper? What about copper? Well, copper is argon,
Is that an exception?
4s1, 3d10. Yeah, it's one of the exceptions you memorize. This is the exception. It's not 4s2, 3d9, it's 4s1, 3d10.
Right.
And so you would expect the charge. This should be fixed charge. What's the fixed charge on this? It should be fixed charge, but it's not. It should be a copper plus 1, which would be argon, 3d10. So it makes total sense. It should be like silver, right? But is copper plus 1 the most common charge on copper? No. Do you know what the most common charge on copper is? Copper 2 plus. Copper 2 plus is argon, 3d9. So now I had this perfect cake, and now I've taken the slice. It's no longer perfect. Is that good? And so why is copper 2 plus more common than copper 1 plus? It doesn't make sense. And so maybe my theoretical understanding is off. Right? I didn't have to do any quantum mechanical calculations. I was just using these patterns to try to figure this out. But it's on. And the reason is, in Chem 1A I didn't say this because I said wait to Chem 1B. In Chem 1B we're going to explain it. How the 3D9 is stabilized. The reason 3D9 is stabilized is because of the structure the copper 2 ions adopt in compounds. And so that's why the 3D9 comes up, and that's why copper 2 plus is fairly common. But, you know, we could memorize all the ions. Okay, copper plus 1, copper plus 2 is more common. But if we have some, you know, we try to blend in some theory into that, maybe we don't have to memorize as much. Not only don't we have to memorize as much, we can also try to make predictions. You know, for example, what do you think gold is? Yeah, plus 1. You'd like to say plus 2, but it's not plus 2. Do you know what it is? It's plus 3. You know, and the situation is, oh, great. You know, that screws everything up because now I got gold plus 3, but there's a reason. You know, gold plus 3 would be a D8, and there's a reason for D8 to be stabilized, which we'll talk about later. And so, yeah, the more, and this is, you know, electron configurations as quantum, but the more theory we can introduce, the better. But sometimes we don't even get to that. Sometimes we just look for the pattern, you know, and then not really try to understand it. We just look for a pattern. And so let's look. So these are monatomic, then we go on and on and on. What I want to do is I just want to hit some anions right now. And so let's take a look at some anions. Get a eraser. So we'll look at some charges here. Let's take chlorine. You know, sodium 2 plus is ridiculous. Well, we aren't going to see it because even though if you did there's a homework problem in chapter 12. If you do that, you'll calculate that it comes as not favorable. You know, to go to the higher charges, it just costs too much energy, even though the lattice is much stronger. What about chlorine? What are the common charges? Well, we have chloride, and then we have elemental chlorine, Cl2. What are the other charges on chlorine? Let's see. Are there any other charges? Is chlorine a variable charge? Yeah, it's a variable charge because we got minus and we got, what's the charge here? 0. Are those all the charges for chlorine?
There might be more, but
There are more. But they aren't monatomic or diatomic like this. They're polyatomic.
Cl+.
Cl plus, you could form that as well, you know, ionization. But you could see it here. You know, this would be Cl plus in a stable form. What's that called?
Hypochlorite.
Hypochlorite. Good. This is a hypochlorite. Do you know what the charge on chlorine is?
+1.
+1. Yeah. Oxygen is -2. Chlorine is +1. -2 + 1 gives us a net charge of -1. What are these called? Oxidation states. Good. And so, yeah, chlorine can have it's minus, it's 0, +1. What else? How about this? ClO2 minus. What's this called? Well, this one's hypochlorite. Hypochlorite. This one would be chlorate or chlorite, or what would it be?
Chlorite.
This would be chlorite. Hypo's one less oxygen. This is chlorite. What's the oxidation states here?
+3, -2.
Yeah, this is -2. -2 times 2 is -4. -4 plus 3 gives us net charge -1. And so here's chlorine in the +1. Here's chlorine in the +3 with chloride. And then we'll go on to ClO3 minus, which is called chlorate. I should have just run it rather than zigzagging here. But let's do the oxidation states. Oxygen is -2 times 3 is -6. -6 is called the net charge. And oxidation states always refer to the charge on a single atom. So on a single atom is -2, we have 3 of them. And so this would be plus 5. And then we'll go here. What's next? Perchlorate. Perchlorate.
+7.
Okay, it's -2. -2 times 4 is -8. -8 plus 7. Plus 7 is correct. And then I'm going to go here. I'm going to go to ClO5 minus. ClO5 minus must be hyperchlorate. Hyperchlorate. Right? Hyper meaning lots. Hyperactive.
There's a lot of choice.
That's a lot of oxygens. Hyperchlorate. Does that look good to you? No. So if you have some, why doesn't it look good to you? If I had a bottle of hyperchlorate, it's very rare stuff. I can give you a good deal on hyperchlorate, right? Why would you think that's ridiculous? Hyperchlorate? You got to be joking me. Why? You got to be joking me. This stuff doesn't exist. Even though I see some, because I do nomenclature. I just did Chem 4 over the summer, but the Chem 4 this summer was really good. But Chem 4 is just beginning, and they have no idea. And so sometimes you see the most bizarre, this is like, okay, there's no way this is going to work, these formulas. This is totally ridiculous. Why is this totally ridiculous? This is totally ridiculous. Well, maybe not, but I think it's pretty ridiculous. Why? At least for stable ions. If you didn't make this, it'd be pretty unstable. be pretty reactive. And why is that? So, we want to go beyond just the straight memorization. Because if we just do the straight memorization, then we can't make predictions like this. Does this exist? Well, I don't know because I didn't memorize it, right? But here, okay, memorization can take you up to this point, but we have to blend it. We have to do the two-pronged approach. We have to add some theoretical knowledge to this. And so why doesn't hyperchlorate exist? Because, I'm the discoverer of hyperchlorate, or maker of it. Why doesn't it exist? Why would you expect this not to be reasonable?
Chlorine's not a big enough atom to
To take that many oxygens?
Yeah.
Well, let's see. What else do we have? We have things like SF6. Yes, sulfur is bigger, but we can put 4 fluorines. Fluorine's about the same size as oxygen. The size, it's not necessarily to do with the size. Oxygens are pretty small. Chlorine's still pretty big. Now, if this was a fluorine, then forget it. Chlorine's too small. Do you see the pattern? The pattern. The pattern. I don't need to know. I don't have to explain this using quantum mechanics. I can just. Well, yes, in a way I do. I don't have to do the Schrodinger equation, right? I don't have to do any math because this is simple. It's not going to happen because oxygen is -2. -2 times 5 is -10, which means that chlorine must be +9. What's special about +9?
It's not plus X, it's just a plus.
Well, chlorine only has 7 valence electrons. If it loses all 7 valence electrons, that's +7. It's got to lose 2 core electrons in addition to get it to +9. How easy is it going to be to lose 2 core electrons? Very difficult. And so this kind of stuff can keep you out of trouble because we know this is not possible. Maybe it's possible. Maybe someone could try to make it, but it would not be stable. It would be terribly unstable versus although perchlorate's not that stable because perchlorate, if you look at that, how many valence electrons did it apparently lose? All 7. Is it going to be happy? It's going to be terribly unhappy. So perchlorate's a very dangerous chemical. It's terribly unhappy. It's very dangerous. And so this is it. If you just do straight memorization, it's only going to take you to a certain level. What you have to do is you have to memorize these things and look for the patterns to take you to a different level. Now, doing that, most people up to this point have just memorized. Memorize the ions, that type of stuff. But, I'll throw in something like this. Maybe you know this, maybe you don't know this. But let's say I asked you, what is the formula for borate? And I've asked this a bunch of times, Chem 1B, Chem 1A. You know what one of the responses I get? Well, that's not fair. You can't ask us that because you never gave us the formula for borate. But, it's not that I want to give you everything that you need to know. You should be able to go beyond. And what do I mean by go beyond? Go beyond is, what is the formula for borate? Do you know the formula for borate? It wasn't in Chem 4, it wasn't in Chem 1A, therefore it's not a fair question. Well, it is a fair question, you'll see this. Borate's very common, like boric acid and eye drops. You should know that. Well, so you might guess, let's guess. BR or B, or what is it? BR? Just B. It wouldn't be, if it were BR, it should be like bro-8, not bor-8. B for boron.
BO3 minus.
BO
Like chlorate.
with a
but
3 minus
chlorate.
charge.
No. BO3 and then the -1 charge.
Then a -1 charge.
That's what I was just guessing.
Yeah, we could guess that, but when I look at this, I automatically I think, oh, this is not going to work. This can't work because oxygen's -2, unless it's peroxide. Peroxide is -1. But Oxygen is minus 2 here.
Uh-huh.
Minus 2 times 3 is minus 6. Minus 6 plus what?
So plus 5.
Plus 5. This
That
is
is
not going to work.
Yeah.
Plus 5 can't work. I look at that and immediately go, that's not feasible. And so, you know, by knowing a little bit extra, you can at least maybe eliminate one. This. Yeah. We'll try again. Try again.
So it has to have a plus 1.
But you probably, the thing is probably how you studied nomenclature. You know, do you see any pattern in the nomenclature rules? Actually, there is a pattern in the nomenclature rule. Maybe you've seen this, maybe you haven't, but let's take a look. Carbonate, what's carbonate? CO3 2 minus. Nitrate, NO3 minus. And then oxate, we'll skip that and go to fluorate. What's fluorate? What's chlorate? Okay, do you know what fluorate is? What, looking at this pattern, what would you guess fluorate is? Well, maybe it's not fair because it wasn't in the Chem 1A book, but it's fair because you should be able to recognize this pattern. What is a fluorate? FO3 minus is correct. Bromate? Not BO, BrO3. Iodate? IO3 minus. And so there's a pattern. And so what would borate be? BO2 minus? Does that look like it fits the pattern?
BO3, 2 minus.
BO3 2 minus? Well, if we did BO3 2 minus, oxygen's minus 2. That gives us minus 6. That means boron is plus 4. Boron at plus 4 sound good? No. I would say BO3 3 minus. If we go BO3 3 minus, then oxygen's minus 2 times 3 is minus 6. Minus 6 plus 3. Is plus 3 okay for boron? Yeah. Gives us 3 minus, and this is it. BO3 3 minus is it. Boric acid would be H3BO3. We could do other things with the patterns. So for example, under nitrate is phosphate. What's phosphate? PO4 2 minus?
3 minus.
3 minus. PO4 3 minus. Sulfate?
SO4 2 minus.
Okay, so I might ask you this. What is arsenate? Arsenate is below phosphorus. What would arsenate be? This one's tricky, potentially. Arsenate came up in the news not too long ago. You know, there's a NASA study for extraterrestrial life, and they're at Mono Lake. And so why were they looking for extraterrestrial life at Mono Lake? Mono Lake is in California, just east of Yosemite. And they're looking for extraterrestrial life because, you know, in Mono Lake there are no fish. You know, it's kind of a dead lake. The only thing that's living in there is the brine shrimp and bacteria. And Mono Lake has high arsenic levels. And so they're looking at the bacteria. They're wondering, you know, these bacteria are living off the arsenic. And so maybe rather than a phosphorus-based life form, you know, we're a phosphorus-based life because we have things like ADP and ATP. Have you heard of those biological energy molecules? So we have those types of things based on linking these phosphate groups together here. But what they're thinking is, since there's so much arsenic in this lake, is it possible, like, unlike all the other life on Earth, that it's an arsenic-based life form rather than a phosphorus. And so rather than having like ADP, you know, what does ADP stand for? Diphosphate. Rather than having adenosine diphosphate, they might have adenosine diarsenate instead of diphosphate. There's maybe arsenic substitutes for that, and if that's the case, then maybe there's life on other planets that might have a different elemental compositional makeup than ours. And so anyway, well, for arsenate to substitute for phosphate, then it's got to be somewhat similar. And arsenate is ASO4 3 minus. So if we see this, then we can figure out what selenate is. What is selenate? What's your guess for the selenate ion? SeO4 2 minus. And so here, the start is we have to have some information memorized. Once we have that information memorized, then we can build up on that, trying to find patterns or trying to use theory in order to supplement it in the multi-pronged approach. And so science is not just straight memorization. It's memorization plus, you know. But you have to have some memorization done, otherwise you don't see these patterns. You know, they don't come up. And so, you know, things like this would be fair game. You know, some people will get it, maybe most people won't. This type of stuff. And so anyway, you're going to have to start reviewing the nomenclature. That's important. You'll have to memorize the solubility rules. That's also important. There are patterns in the solubility rules to help you. You know, for those of you who memorized it, have you seen the patterns in the solubility rules? You know what the patterns are? Because not every compound is in the list of solubility rules. So if you're given a compound that's off the list, like for example, I gave this compound. And I asked what's the solubility. This is back in Chem 1A. It wasn't last semester, it was many semesters ago. But I clearly remember this problem because a student came up to me afterwards and said, hey, wait, oxides were not on our list of solubility rules. This is not fair. You know, and so I got heavy complaints about this, and I thought, wow, unfortunately, my point didn't get across. You know, yeah, it's not on the list, but you should be able to figure it out based on the pattern, right? In fact, oxide should be even less soluble than what's on the list. What was on the list? Sulfides. Oxide should be even less soluble because of Coulomb's law, right? And so, unfortunately, they didn't get it right, and so that's what the complaint was, but it's insoluble. It's insoluble because we know about bonding, we know about charge, and this type of stuff. And so you can make predictions. This is what we do in science. So in science, we don't always understand the theory totally, or the theory might be too complicated, but we use these patterns to make or deepen our understanding. Must be missing something that I talked about. All right, this week, like I said, we're jumping into it. The jumping into it is we're going to start off trying to recognize some patterns in chemical reactivity. In other words, we're going to be observing or analyzing a whole bunch of chemical reactions, so we get an understanding of these types of things. And so, oh, I know what I was going to say. So I'll talk more about the class and like the requirements, exams, and that type of stuff tomorrow. But today you'll want to start reviewing. One thing, though, I need to bring up now, so we can take a look, is I'm going to start using. This didn't come up this morning. Computer issue. But we're going to be using this site. Hard to read, but it's called Piazza. I sent out an invitation. Did you guys check your El Camino email? And so you should have gotten an invitation for this. If you didn't, you still can sign up. You don't need an invite. All you need is an access code. And so if you just go to sign up, and then you put in El Camino, I think I'm the only chemistry class in here. Let me check.
Is it mandatory?
No. It's not mandatory, but you'll have to ask a friend for information on this. The type of information you'll see, okay, here. So we just need the class access code. Class access code is just Chem 1B and PLC. Chem 1B. And that'll get you in. Let's log in. So can you guys see this? A little bit?
Yeah.
All right, you want to, so slow. You want to go in here because I posted some stuff in here. There it is. So, like the handouts, I'll hand these out tomorrow. The course info sheet, syllabus. Then I have these. This is what I'm going to start tomorrow with. You don't have to download these, but I have some PowerPoints here. 3 PowerPoints, chemical properties, and then a couple of other handouts. One is chemical reactions homework, your first homework assignment, and then redox and acid-base strength here. And so those you don't absolutely need those, but pretty helpful. Some lab handouts. I'm not going to talk about these until later on my office hours. And so there's some posts here. You can post stuff here if you have questions. I'll try to answer those, or other students can answer those as well. So take a look at this today, and then if you want, download the PowerPoints, which I'm going to start with tomorrow. All right, so let's talk a bit about the nomenclature here. And so there's some 8s that follow the pattern. It's a periodic table pattern, but there are some 8s that don't fall on the periodic table pattern. What 8s do you need to know? The 8s would be the anions. The anions are either going to end in "ide," "ate," or "ite." You only have 3 choices. And so what other 8s do you need to know? Permanganate, chromate, dichromate, acetate, oxalate, all those. There's some ides that are off the periodic table, like chloride. There's some ides that aren't. Hydroxide, peroxide. The ites are typically derived from the 8s. The ites are 1 less oxygen. Hypoites are 2 less oxygens. Perates are 1 more oxygen. And so you'll review that, review bonding, review quantum a little bit so you can understand bonding a little bit more. And then we're going to get into this. what is chemistry? What do chemists do? What do you say? What do chemists do? Chemists study the atoms.
Electrical interactions between atoms.
Yeah, pretty much electrical interaction is the most important. That's why Coulomb's law is so important. The chemists study matter. What do they want to know about matter? They want to understand the properties of matter. And what kind of properties are there? There are chemical and there are physical properties of matter. And so, for example, this. What are the chemical properties of sodium chloride? I can tell you some physical properties of sodium chloride. Is sodium chloride soluble in water or insoluble in water? It's soluble. All sodium salts are soluble. In fact, group 1 and ammonium salts are soluble. When you go back and review the solubility rules, the easiest is the Chem 4 solubility rules. The Chapter 5 solubility rules are more involved. And so I would suggest the Chem 4. If you haven't had Chem 4 here, I'll try to post those, or actually maybe I'll write those here. And so if we go back to the Chem 4, not the Chapter 5 solubility rules, what were they? First we look at the cation. If the cation is group 1 and ammonium, they're all soluble. Okay, after we look at the cation, then we look at the anion. That's the easiest way of doing it. When we look at the anion, what anion do you look at first? Not the halogens. The halogens are more exceptions. This group has fewer exceptions.
Phosphate?
No, phosphates at the end.
Acetate?
Acetates, chlorates, and nitrates. These are soluble. It doesn't really matter what cation you put on this should be soluble. There are some exceptions. This is why there are rules. Like mercury 1 nitrate's not so soluble, but we'll just throw it in this pile here. Okay, after we look at acetates, nitrates, and chlorates, then what? Then now the halogens. Fluorides, bromides, and iodides. What happened to fluorides? Is it time?
We got 3 minutes.
3 minutes? Okay. I see people gathering out downstairs. So we got chlorides, bromides, and iodides. What about fluorides? Why aren't fluorides on this list? What makes fluoride unique? Not its electronegativity. Fluorine's electronegativity is very high. We have to be careful about electronegativity, because there's a difference in electronegativity. And so if we look at chlorine, chlorine has fairly high electronegativity. Does chloride have the same electronegativity? Like fluorine's the highest. Fluorine is a 4.0, chlorine's a 3.5 on the Pauling scale. Chlorine's a 3.5. Is chloride a 3.5? No. Is chloride higher than a 3.5 or lower than a 3.5? Yeah, much lower. It's electronegativity. Why does chlorine want another electron? Does chlorine want to form 2-? Well, because the definition of electronegativity is the ability to attract electrons. So does chloride really want another electron? No, it's not. It doesn't have to do with electronegativity because fluoride's electronegativity is way, way, way lower than 4.0. Right? Does fluoride want to attract another electron to form F2-? No, it's just like this. So it's not electronegativity. It has something else. And this is why I want you to review Chapter 12, the bonding at the end, lattice energies and that type of stuff, and Coulomb's law in the appendix, so that you can understand. It has to do with the not the electronegativity, but the Yeah, the bond strength because of its small size or large size? Because of its. Let me ask you this: which is more soluble? Sodium. Actually, let me pick something that's not going to be as difficult. Let's go with. This is tricky because the bonding is a little bit tricky. All right, let's go with magnesium chloride and magnesium fluoride. We have these two. You know, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. But when you look at this, both of these are soluble. Which one is more soluble? Which one would you predict to be more soluble? The chloride should be more soluble. Why? Well, on the one hand, the chlorine should be more soluble because it should have a weaker lattice. It should have a weaker lattice. Why? Because it should have weaker bonds. It should have weaker bonds because of the size of the ions. What we're looking at is we're looking at a +2 ball being attracted to a -1 ball. And so chloride's this -1. Fluoride is this. And so when we look at this, what I call this, I don't know what your Chem 1A, if you have a -1 spread out over a larger sphere versus a -1 spread out over a smaller sphere, then the difference is they both have the same charge, but they have different charge densities. And so something like fluoride has a higher charge density because the negative is more concentrated, versus here the negative is less concentrated, and so that's going to make a difference in the ionic bonding. And so all these topics are going to come into play in Chem 1B. So if these are a little rusty, or if you've forgotten about them, then you want to review all this stuff because we need all this stuff when we start talking about the properties of this. Because I might start asking you, what are the properties of magnesium chloride versus magnesium fluoride? Well, we're taking chemistry. What do chemists do? Chemists study matter. What do they study about matter? They study the properties. How do they understand the properties of matter? Well, what we have to do is we have to start thinking in terms of, do you want to memorize all the properties, or do you want to try to have some kind of theoretical? Well, what we want to do is we want to have the more theoretical, the less memorization we have to do. And so you better start reviewing some of this theoretical knowledge so you don't have to memorize everything, basically. And so I know this was kind of a random mismatch of things, but I don't know exactly what you guys forgot and what you guys remember from Chem 1A, and so it's up to you to go back and review the stuff that you've kind of forgotten about. And then tomorrow we're just going to start with new stuff, no more review. Okay.